Okay, good afternoon, everyone, and welcome to today's seminar. It's a great pleasure to have Professor Donna Weinstein here with us today from Purdue University, Electrical and Computer Engineering, where she's also a senior fellow of the Kroc Institute for Tech Diplomacy. Professor Weinstein is a Purdue faculty scholar, and her work has been recognized by many awards, including the NSF Career Award, the DARPA Young Faculty Award, First Intel Early Career Award, and the TRF Transducers Early Career Award. Professor Weinstein's research is focused on innovative microelectromechanical devices for applications ranging from MEMS IC wireless communications to micro-robotic actuators and ultrasonic stimulation. So it's very exciting to have a chance to be able to learn more about her work today. But before I hand it over to Donna, I just want to remind everyone in the room, feel free to ask your questions anytime. Those who are listening to us online, you can type your question in the Q&A box, and I'm going to keep track and ask them on your behalf. There is a reception at the end, so do stay with us for the reception. And with that, Donna, we're very excited to hear your talk.
Right. Hi, everyone. Thank you so much for that kind introduction, Farnaz, and for inviting me to come and speak with you all. MIT was my home for many years on the faculty here in MTL. It's been a wonderful move to Purdue, but it's really fantastic to be back and get a chance to connect with everyone. So I want to focus today, as Farnaz mentioned, my research group has several different areas that we're focusing on, but one of the big overarching themes for us over the years has been in integrating MEMS or micro-electromechanical resonators and building blocks into standard integrated circuits. And this has been work that we began here in MTL, including some of the students who worked on this over here, but we really had a lot of success and pushed through as well at Purdue. So this is the work of many students over many years, and we've certainly learned a lot, and hopefully I can share some perspectives on all of that, and then looking forward at exciting opportunities for this field. So as I mentioned, we really focused on acoustic resonators, and one of the key areas that really necessitated integration into circuits side by side with active devices was in scaling resonators to very high frequencies of operation, gigahertz frequencies of operation. And the primary motivation for that was in on-chip frequency sources, think microprocessor clocks, for example, filters for radio front ends, and sensors, all built into your standard CMOS circuit technology. Pushing to gigahertz frequencies of operation to RF and millimeter wave regime opens up new opportunities where there's a dearth of hardware solutions. So if you have these frequency sources and basic resonant tanks at these frequencies, there are plenty of opportunities with automotive applications, including sensors, but also autonomous vehicles and the sensors necessary for that. 5G and 6G communications, wireless communications, terahertz and millimeter wave imaging, spectroscopy. You can think about smart infrastructure and the improvement in size, weight, power, and cost, or SWaP-C, as some of you guys may have heard, when it comes to scaling down sensors and then building in radio communications between sensors to create sensor networks that makes smart infrastructure possible. And then other crazy ideas, like when you have a bunch of these oscillators with very low phase noise on chip, and you can make one, you can make 100, you can make 1,000, you can couple them together. You can engineer in non-linearities and various things like that. Then there are opportunities for non-Boolean signal processing and computation. So not just ones and zeros logic elements, but oscillatory logic is an example. And then, of course, quantum computing above 4 Kelvin, right? So for those of you who are in the quantum space, H bar omega is the energy associated with something that's oscillating at some frequency omega, equals kT, Boltzmann constant times temperature. Well, if you're up at 80 gigahertz, then you don't need a dilution fridge anymore to get to the quantum ground state. So lots of different opportunities to leverage these building blocks. Why do we want MEMS for these resonant tanks? Well, there are several benefits. I already mentioned the small size, weight, and power, right? So first of all, they have very high quality factor. This means that as a mechanical structure is vibrating in these high quality materials like silicon and other ceramics and high temperature materials that you find in the front end of line, for example, in CMOS, those acoustic vibrations are a lot less lossy than, for example, the electrical LC tanks, inductor capacitor tanks, where electrons are sloshing back and forth between the inductor and the capacitor, which is resistive and therefore lossy. So it translates to very pure resonance at a very sharp frequency, as opposed to spreading that energy out over a variety of frequencies or range of frequencies. They have small footprint relative to their electromagnetic counterparts, obviously because acoustic waves are much slower than electromagnetic waves. And so the wavelength corresponding to a particular frequency is orders of magnitude smaller. And then they have the capacity for wafer scale fabrication and packaging. And that is very critical for size, weight, power, and cost, and allows you to reduce form factor and achieve that integration on a larger scale. So how do we make these MEMS high frequency resonators come about? Well, there are, if you look at pushing to the gigahertz regime, right? At low frequency, we've got AM radio, right? In the mid band, FRAM radio, GPS, Wi-Fi, the things you're typically seeing. In the high band, above 6 gigahertz, there's this huge open opportunity for new hardware, right? But it's also a major challenge. Why do we lack that hardware in this frequency range? There are some key challenges and holy grails in designing RF MEMS resonators in this space. So what do people want to get to 5G plus broadband communication, to MIMO, to massive IoT, Internet of Things, and autonomous vehicles and all that? First is high electromechanical coupling, right? So we want to feed in an electrical signal from an antenna, from some other part of your circuit, induce mechanical motion that has all of these benefits that I talked about, and then convert it back to an electrical signal to do something useful with the rest of your circuit, right? And so that conversion from electrical to mechanical to electrical, that there's a transduction efficiency associated with that. You sometimes will hear that referred to as K squared, but you want as high as possible, right? And typically we're talking about, for example, the film bulk acoustic resonators in your phone. They're made of aluminum nitride or scandium doped aluminum nitride. And you have like 20 of them in your phone right now for all of the different filter functions. That has an efficiency of about 10%. Energy converted from electrical to mechanical and vice versa. But that translates also to a bandwidth of your wireless communication. So how fast can you download a video or to watch your TikTok, or nobody's doing that anymore, right? But stream your content and so forth, right? You want as high bandwidth as possible. You want that in a very challenging spectral mask, because there's some band that's committed for certain wireless communication here and another here. And so you have all of these little fractions of bandwidths that all have to come together so you can get your maximum data transfer rates. So that's one benefit of going to higher coupling. You can get higher bandwidth filters, lower insertion loss, improved signal-to-noise ratio when it comes to sensors. So that's one big feature of getting high-frequency resonators. Another is, again, this is the wish list moving forward, tuning and programmability. Okay, so I want these high-Q resonators. I want them to be really efficient at converting energy from one domain to another, but I also want to be able to tune them in frequency, by the way, across like octaves, ideally, and to be programmable, so I can do whatever ad hoc system I want. That's obviously immensely challenging and something very interesting for us to be thinking about how to make that happen. But it enables things like ad hoc radios and new ways to do computation and even cognition. And then through all of that, we also have to think about operating conditions. So I might be working in a harsh environment, for example, where I have to think about the effects of temperature and pressure, G-forces, radiation, whether I'm in an aqueous or other chemical environment that is going to limit the material choices, limit stability, reliability, and lifetime of my devices. So I need to think about all of those things as well. We also need to consider that in the context is going to higher frequency, our films and structures become smaller and more susceptible to scattering and various other things as these vibrations start to become more surface instead of volume driven. And so those are kind of all things that need to be considered. Okay, so with that context, right, what do MEMS resonators look like today? So if you look on the left-hand side here, there are a couple of examples. There are a lot of different flavors of MEMS resonators, but these are nicely representative. So you could, for example, design a structure that will vibrate with a particular longitudinal expansion and contraction, right, based on the thickness of a film. So one example of such a device is the dual Bragg bulk acoustic wave resonator, or BAW device. This is an example from Texas Instruments, where instead of typically your MEMS devices will be suspended in air or vacuum or something through some special fab process. Of course, that has to get packaged to protect the released device. In the case of TI, they said, never mind that. We only have one frequency we care about for any particular device. I'm going to make acoustic Bragg reflectors that basically form a mirror. And even though I'm not suspended, will generate reflections and prevent vibrational losses into the substrate, whatever this thing is sitting on, okay? So that packaging becomes easier, it becomes more robust in, for example, the case of acceleration forces that are present, and easier to fabricate. And so piezoelectric thin film will be sandwiched between electrodes, and then these mirrors, acoustic mirrors, above and below. For those who don't know what a piezoelectric is, it is a material that's used quite often in MEMS technology, that based on its crystal structure and its lack of symmetry, when you apply an electric field across it, it actually generates a strain in the film, or vice versa. If I strain the material, basically it'll generate an electric displacement, which gives me charges above and below, and I can use that to measure the strain out, generates a voltage across the device. And so very nice to implement those directly for MEMS devices because there's a direct conversion of energy. Another example of a kind of resonator you might see today is, this is an top view scanning electron microscope of a lithium niobate based resonator. So that one is aluminum nitride, like the filters in your phone today. This is lithium niobate. You also have lithium niobate filters in your phone today, but they're surface acoustic wave structures. So this is kind of next generation, but using the piezoelectricity of lithium niobate or other materials with suspended structures that then will resonate, in this case, by lithographically defining the pitch of electrodes, basically how far apart the electrodes are spaced together, will change the frequency. So here I have a fixed frequency for my entire chip because I've put down these films one on top of the other. In this case, I can define patterns which will define the frequency and get multiple frequencies on a single chip. So piezoelectricity, fantastic, gives me strong response, but these approaches do have major limitations, specifically specialized fabrication processes and packaging requirements. But then also these materials are, at least for now, not CMOS integrable. So I need multiple chips in order to get my ASIC, basically my support circuitry, my drive circuitry, and perhaps any other parts of the radio front end in that case, and a separate chip for all of these resonant tanks. And so you can imagine, well, I'm going to need to combine these chips somehow. I need my maximum frequency that I can operate at depends on the bandwidth of the interconnects between these chips. And creates other vulnerabilities as well. Packaging stresses that change the behavior and the frequencies of these devices. Our approach has been to kind of leverage what's existing in CMOS technology already and hack the process in order to build in these acoustic waves into the CMOS stack directly. So this is an example of, just a cartoon of what our IC integrated MEMS resonators would look like, where we, again, are leveraging the standard process. So it's essentially free, no modifications to the CMOS stack, no post-processing, no release step. It allows you to leverage the very, very fine, lithographic features that CMOS spent billions of dollars to get going with those extreme UV lithography systems that you've heard about in the news, and that's the bottleneck for moving forward with semiconductor manufacturing capabilities and scaling those up, so we don't depend on supply chain limitations, and we can't get our cars or our laptops in a timely manner because there's a shortage of chips. Well, we can use what CMOS already has and scale to very small dimensions and therefore very high frequencies. And then it leverages the active devices, transistors, essentially, that are built into the CMOS process in order to improve performance, along with all of those metal layers above, which also are really, really hard to achieve in a specialized foundry, but are available in CMOS. So that's the big picture. If we can get these integrated, MEMS devices at high frequency integrated on chip in CMOS, then it opens up so many opportunities. I already mentioned next generation wireless communication, right, which needs these millimeter wave high Q, high transduction efficiency resonators, right? But that enables things like autonomous frequency agile radio front ends that can even do things like inherent spectral sensing, right? If you engineer the linearities and nonlinearities correctly in these devices. In the Internet of Things, I mentioned low swap-C sensor nodes, which creates opportunities for embedded sensors, physical, chemical, environmental sensors, and so on, and provides opportunities for things like in-sensor computing, computation at the edge, so you don't have to communicate so much between sensor nodes. You could do some decision making on each sensor, and then the requirements for the links themselves can be much lower. But there are also new opportunities that are created when we think about making these ultrasound transducers, embedding them inside the CMOS chip. So first of all, on the hardware security side, a couple of notes. So if I'm making a clock for a microprocessor, for example, right now that clock is a quartz crystal. It's off chip. It's this bulky component. You know, if you open up your old watch, don't open up your iWatch, please, your Apple Watch. That will void the warranty. But even that has a quartz crystal, which is separately packaged and it's low frequency, and it's wired into your microprocessor chip, and it's connected through a phase lock loop, multiplied up in frequency to get to that 3 gigahertz microprocessor clock capability and all of that. It's a whole thing. And then that clock gets distributed throughout your entire microprocessor. It takes a bunch of power. But in any case, that wire to connect your quartz crystal to your microprocessor clock, well, someone who doesn't mean well could interfere with that pin and glitch your clock. And as soon as they do that, you've compromised the entire security of that microprocessor. So it's a major vulnerability. On the other hand, let's say, so if I could get the clock, that LC tank, essentially the resonant component on chip, there's no pin to interfere with. Plus it's at higher frequency already, and you're not multiplying up noise and so on. So there are benefits to that integration across the bank. But another opportunity is actually in imaging the chip. If I have these structures that are generating acoustic waves, that can sense acoustic waves, I can basically have ultrasound imaging of my chip from within the chip, even after it's packaged, even after it's been deployed in the field, right? So I could actually monitor various things. I could see if, when these microchips are created, are fabricated, you get some part of it done in one foundry, then shipped off to another part of the world for dielectric deposition, another part of the world for back end of line, another part of the world for packaging, and so on. And the chain of command of these chips can create vulnerabilities. Someone can put in a Trojan, or more amicably, let's say after packaging, now that we're going to these various more complicated packaging solutions like 3D heterogeneous integration, 2.5 DHI, thinking about stacking chips together and so forth. Well, how do I monitor that my interconnects between all these different chiplets, for example, are doing well? How can I figure out what's wrong with my chip? If I can image from within it, that's another huge benefit in terms of hardware security. And of course, if I have ultrasound transducers in a microchip, I could do biomedical imaging, stimulation, diagnostics, and therapeutics, right? So there are various ways in which this can be helpful. Okay, so back to basics. How do I actually make these integrated resonators in CMOS? I want to launch acoustic waves within electrical signals, and then I want to detect them. So I want to drive vibrations and I want to sense them. If we look at what's going on in CMOS today, the typical technology platforms that you can tape out in, right, with TSMC or Global Foundries or Intel or TI or so on, you will see certain features that allow you to drive and sense vibrations. So I put capacitive air gap in there as just a possibility. Obviously, most technologies do not have any air gaps. It's just solid, materials stacked one on top of the other and so on. But just as an example of what typical transduction looks like, if I have a parallel plate capacitor, I apply a voltage across it. What happens? I have equal and opposite charges. They're attracted together. They pull together. That is motion generated from an electrical signal. That's electrostatic transduction. Okay, I can wiggle that voltage and get the thing to vibrate. Okay, so in most cases, we don't have air gaps, but we do have dielectrics, for example, the gate dielectric, or maybe a MIM capacitor, metal insulator, metal capacitor, right? Those are available in CMOS all over the place. And so similarly, if I apply a voltage across that. I instead of pulling the plates together, well, I'm straining the dielectric, right? So similarly, a little squeeze. And again, I apply the oscillating voltage and I launch acoustic waves into my CMOS-stack. So I can drive and I can sense that wave. So similarly, fixed voltage across the parallel plates, but they're vibrating. That has a change in the gate dielectric thickness, or the dielectric thickness changes the capacitance, dq dt, corresponding to that change in charge with time. I can get a current out that measures essentially the motion of my structure, which is what I want. But gate dielectrics and MIM capacitors are not the only capacitors in CMOS. I could get a PN junction, and if you remember back to your semiconductor physics, there's a depletion capacitance associated with that. That will also generate strain in those fixed ions that are in the crystal lattice and generate strain, and similarly, you can get a change in charge if the structure is vibrating. So that's both drive and sense. If I use thermal, well, I can drive acoustic waves with a thermal signal. So I basically run a bunch of current through a resistor or through my transistor. I heat things up. Okay, not the most elegant solution, but that thermal expansion will, cause the structure to change. Obviously, typically at lower frequencies than what I could get electrostatically. Typically, thermal timescales will be on the order of microseconds to milliseconds, depending on the material and depending on the size. But I can't sense it. Entropy doesn't work that way. Okay, piezoresistively, I could sense vibrations, right? So piezoresistance corresponds in materials like silicon. If I strain the crystal, I change the mobility. Or if it's in a metal, I'm changing the geometry, making it longer, smaller cross-sectional area. That changes the resistance, and I can measure current that way. And then transistors, well, they combine both piezoresistive and capacitive elements. So if I'm straining a transistor, I will get a piezoresistive effect. So the mobility of my drain current will change, and my capacitor, my gate capacitance changes, so I get a field effect. And the combination of those two actually can help us to scale to very high frequencies with simple two-port measurement. And so that's what we did. We used capacitive transduction using basically MOS capacitors, taking transistors, tying the source and drain together, and getting individual MOS capacitors to drive acoustic vibrations, and then sensing using a couple of transistors in the middle of this array that would give us differential drive, differential sense with this array of transistors in CMOS. So again, just as an example of what we were able to do, we demonstrated these devices across multiple platforms. This is an example in IBM at the time, now Global Foundries, 32 nanometer SOI process. We were able to get 3 gigahertz, 3.2 gigahertz acoustic resonance, quality factors over 13,000 in those cases, and on-off capabilities. All right. But we also were able to push this off to FinFET technology. So some of the most advanced technology nodes that were certainly available at that time. Now 14 nanometer seems like a thing of the past, and we're getting into discussions are happening on 7 and 5 and 3 nanometer technology, but still kind of very, very advanced lithography capabilities and high frequency transistors. So with this and arraying these transistors, similar concept, capacitive drive, transistor sensing, we were able to demonstrate over 30 gigahertz acoustic resonance with Qs in over 1,000. So somewhere close to the material limits of silicon in terms of the loss mechanisms that were in place. All right, so with those FinFETs, the 32 gigahertz mode that I showed is actually expanding and contracting along the fin width. we could do multiple things. There are different vibrational modes that can exist. In the FinFET case, we also demonstrated resonance along the fin length, right? And we were able to study, so those were kind of longer wavelengths, demonstrated some 11.8 gigahertz devices using that, and worked on, designing the entire structure in order to support those vibrational modes. So how do we do that? So we talked about how to drive and sense. How do we confine the vibrations to where we want them to be within the CMOS stack once we have these acoustic waves? So this requires kind of dispersion engineering, and it's analogous to what you would see in photonics or in surface acoustic waves. Basically, it's a matter of engineering the impedance mismatch of materials and forcing your vibrations, or in the case of photonics, your electromagnetic waves, into particular layers and particular modes that correspond to particular frequencies. So when you think about fiber optics or photonics on chip, you're talking about cladding layers with high and low impedance that confine the vibrations. Same with surface acoustic waves that have layers engineered to confine the vibrations in, near the surface and get the maximum performance. In CMOS, we don't have the luxury of choosing our materials. We don't have the luxury of choosing the thicknesses of our layers, right? We only have lithographic definition. So we can define geometries in plane. But we have multiple layers to work with. We have high contrast between the metal layers and the background low-K dielectric. We have the business end of our devices where we actually want to confine the vibrations at the transistors. This is where we're driving the acoustic vibrations, and this is where we're trying to sense them. So what we'd like to do is launch acoustic waves in this front end where all the transistors are, and then ensure that the vibrations stay in plane and that they terminate at some point, okay? So first part was getting the in-plane vibrations, making sure we don't lose acoustic waves above to the metal layers or down below to the substrate, right? And so this involved basically engineering that entire stack. And you see we have this periodic structure because that's what we can play with in the back end of line. So we have this phononic crystal waveguide that's generated to create these slow wave structures, essentially, that prevent vibrations up or down. So engineering that's actually really, really challenging because, again, we don't have any control over the number of layers, the thicknesses of each layer, and there are limitations we have to work with within the constraints of the foundry, design rule constraints or DRC constraints, if any of you have ever taped out in a CMOS chip. And so in addition to that, the process is the geometry is actually quite complicated. And so we didn't have the computational power to design the entire structure altogether. So we do this piecewise thing. We know we're trying to find frequencies that will survive, that will be guided in any particular CMOS stack, given the layers, given the materials. So we make unit cells. We find the dispersion relations associated with unit cells and kind of piece it all together to find those bands where frequencies cannot propagate. Okay, so this is just to show a snapshot of what that would look like. I won't go into the details here, only to say it's quite complicated, and given the number of parameters, this would be a wonderful place to interject some artificial intelligence in optimizing the geometry of these devices. Okay, so that's generating these acoustic waveguides, these slow wave structures that will not propagate up into the metal layers and will not propagate down into the substrate. How do we get lateral confinement? So in this case, the periodicity, you saw we have many, many periods in plane, right? And the reason for that is that I need to create that, that slow wave structure, but it depends on the unit cell in plane. If I change the length of each of those cells, the periodicity, I actually change the frequency that can propagate in that phononic waveguide. And so if I change the periodicity of these structures, this is a wavy picture here because that's just the way the SEM came out. But you can see that I have a particular width to these devices, and it gets a little longer here. And that's to give us this mismatch, and is in fact an adiabatic transition in that case, from where I want the resonance to exist and where I don't, where I want it to terminate. So we looked at various different examples of how to make that lateral transition, gradual and abrupt transitions under different gate lengths. So you could, the gate length, as I mentioned, we're vibrating in this dimension. So if we have a longer gate, then we actually have a lower frequency. And you can see a cluster of devices with lower frequency here, cluster of devices with higher frequency corresponding to these different gate lengths. But you can also see some sharper peaks, and then some peaks that have, or some modes that have multiple peaks, where an abrupt transition from phononic crystal beautiful waveguide where my device can exist, and then boom, nothing, no PNC at all, no waveguide at all, right? That creates an immediate scattering point, which creates a bunch of other modes. And so that adiabatic transition is very important for us, for high Q mode. Okay, but through all of this, we have some major challenges. So if you look here at this axis, this is the electromechanical transconductance. This is basically us applying an AC voltage and getting it to the drive capacitors and measuring an AC current out of the transistors corresponding to the vibrations, okay? So that's this transconductance, and it's in micro-Siemens. It was nano-Siemens in the case of 32 nanometers. Okay, so this is a huge improvement, but still too small to close a loop and make an oscillator at these frequencies. So some challenges there. But looking forward, there are a lot of exciting opportunities to leverage emerging materials in CMOS. And a lot of these we can leverage from CMOS foundries investing and developing these materials for other purposes. Specifically, there's a lot of excitement in case of non-volatile memory, where materials like ferroelectric films, which have hysteresis built into them in terms of polarization, domain up or domain down. There are phase change and phase transition materials that people are looking at, and these often exhibit a large volumetric change when they undergo that transition. There are opportunities for magnetostrictive and even optomechanical coupling between these other domains and mechanical signals. So here, I'm going to focus on ferroelectrics. Ferroelectrics are piezoelectric, just like the aluminum nitride and lithium niobate that I talked about. It's a direct energy transfer from a field to a strain and vice versa. And so, and they are front runners for non-volatile memory at front end of line. The industry spent a lot of time looking at ferroelectric materials for logic, People were looking at negative capacitance transistors, which had sandwiched ferroelectric and dielectric films that gave a really steep subthreshold slope. That's kind of gone off a little bit in terms of the industry interest. But for non-volatile memory, it's still a very exciting opportunity. And they spent all this time and all this effort developing these ferroelectric films, which have this bistable state, essentially, and why not use it for memory devices? So that's not a new concept. Texas Instruments, back in the early 2000s, had this in back end of line. So they made ferroelectric capacitors back in the metal layers using PZT, lead. Okay, that's not something you would normally see in your CMOS, but it's in the back end. It's low temperature processing, so it's not so bad. It's after all the transistor bit is done. And so there's no high temperature steps at that point to infuse in the lead and other yucky things into your transistors and ruin them. But like I said, people really looked a lot at integrating ferroelectrics into the front end of line. And so you can see all this literature, and we know all this development to product and close to launch for ferroelectric films in CMOS front end, which is very exciting because remember that transistor sensing I mentioned and how that gate dielectric gives you the field effect. Well, imagine if that field effect is actually from a piezoelectric, which is going to give you a much stronger response, and it's amplified by the transistor transconductance. Right? So then you get this beautiful boost in performance by at least 1,000x. Most of the materials that have been looked at, I think most recently, the front runners are HZO, that's zirconium-doped hafnia, or silicon-doped hafnia. And so those are being explored front end, back end of line for 3D HI, heterogeneous integration, and so forth. Now, ferroelectric transducers are not a new concept in our world. From the MEMS perspective, people have looked at ferroelectrics. They're exciting not only from the hysteresis, from their piezoelectricity, but also from that tunability perspective with their nonlinearities that are inherent to the device. So people have worked with HZO, scandium-doped aluminum nitride. When you go high enough on scandium, it's not just a stronger piezoelectric film. It actually builds in this ferroelectric property, PZT and BST. And we used that old TI process. Actually, Dennis Buss, when he was a visiting professor here, and he was a TI fellow. He gave us access to their technology, which is not an easy thing to do with TI, but gave us access to their ferroelectric process. And we were able to demonstrate the first CMOS-based ferroelectric MEMS devices out there. And so genuinely monolithically integrated ferroelectric devices I'll discuss more in just a moment. Between BST and PZT and HZO and AlScan and all of these competing potential materials for ferroelectric transducers, there's various optimization that has to be done. And it's often discongruent with the optimization that's done for CMOS non-volatile memory. CMOS wants to go really, really thin, so you can get very low voltage switching, which means low power memory switching, right? But in MEMS, we actually want a large volume of our vibrational mode to be piezoelectric, so I get better transduction efficiency. But when you go thicker on these ferroelectric films, they lose their ferroelectric properties. And so there's this interesting material optimization that has to happen. And we don't need those same memory devices as the MEMS devices, but they do need to coexist in the same process. And so something to think about. So you want low coercive voltages, but long-term reliability. So the critical fields, the coercive field versus the breakdown fields in the devices, again, also have to be considered, along with things like interface states and so forth that can create instabilities when you're thinking about making clocks or making filters or making sensors with these devices. Any charge effects and things like that can cause problems. All right, in the interest of time, I won't go into the details of how how we designed specifically these ferroelectric capacitor-based resonators, only to say that the same concepts that I talked about for kind of front end of line CMOS devices, where we array a bunch of these transducer elements together, design these acoustic waveguides within the CMOS stack, right? And change the periodicity to change basically how wide these structures are and how and the spacing between them in order to define the frequency. It's that same concept. In the case of these ferroelectric capacitor-based devices, there are all sorts of opportunities to leverage that hysteresis and the nonlinearity. And so depending on the bias voltage that's across each one of these, you can pull the film up or down, which changes the phase with which, if I apply voltage, do I strain or do I expand that little segment of my structure? So you can imagine I can excite different modes. I can, by changing the polarization on these devices. So we were able to demonstrate pole zero switching. If we look at frequency versus basically the amplitude of vibrations of the structure. So this is basically a transfer function from one port to another port across the device. And we were able to demonstrate with the voltage that's applied a change, basically a analog switching of the peak and modify that. We were also able to show frequency shifts in the device corresponding to the mechanical properties of the PZT as you change the bias voltage across it. So you can see the pieces of the puzzle starting to come together on programmability and tunability of these devices. Now, if you've ever done any radio design or if you've ever made a filter of any sort, then you are probably interested in linearity. You want your wavelength coming in, your frequency coming in, to be preserved as a frequency coming out. So understanding that linearity of these ferroelectric transducers in this very nonlinear hysteretic film, very important, right? Where do I want to bias that pulling of the film in order to get maximum linearity when I'm trying to make a filter? Where do I want to bias it for maximum nonlinearity if I want to do non-Boolean computation? So understanding the large signal model of these devices is very important. So we spent a lot of time working on that as well. Again, in the interest of time, I won't go too deep into it. You can refer to our paper on the archive currently under review for that large signal nonlinear model. And in all of these CMOS devices, we basically have to hack into the models that are provided by the foundry, add in our electromechanical response, and then kind of package that all together so I can simulate, use the powerful simulation tools that are available in CMOS and Cadence and various others in order to build in that electromechanical component. But large signal nonlinear has to be built into that. Okay, so that's with current technologies. There's exciting opportunities in materials. There are also exciting opportunities in device architectures. So geometries are constantly being reinvented in the foundries now, right? People are working hard to get more and more than more. And so, this was FinFETs. We did 14 nanometer FinFETs. This is 7 nanometer FinFET technology. And you can see the fins. This is a cross section. So this is the silicon gate dielectric, and then the metal gate is wrapping around it. But that's like a thing of the past now. People are looking at nanosheet FETs, and then so thinking about how to scale down to 5 nanometers, 3 nanometers and beyond, and keep that electrostatic gate control of your semiconductor gate all around, and then stacking on top to get the current density that you need. And then complementary FET is kind of the next wave. You can't find SEMs easily of that yet, so because it's new enough, but stacking NMOS and PMOS on top of each other and creating structures like that. So you can imagine this starts looking like our phononic crystals, but now in the semiconductor, you can imagine the boost in signal when we get access to that. So if anybody online or elsewhere has access to this technology node, let us know, please, so that we can do that demonstration, because the performance should be pretty outrageous. Okay, so a couple of kind of thinking about, this is where silicon is going. But silicon is not the only integrated circuit technology out there. Not only that, we are now in this huge semiconductor wave with a huge influx of interest from the government on a national defense level, but also from the foundries that are getting de-risked by funds coming in from CHIPS Act. Everybody's looking at packaging, at manufacturing, at 2.5D, 3D HI. People are amenable to using the best material for the job. And so we can think about not only silicon, but other integrated circuit technology opportunities. Gallium nitride is one that we have been working in for quite some time, including, this is a monolithic oscillator fabricated here in MTL Building 39. MIT.nano was not yet a hole in the ground, just a concept in Vladimir's beautiful brain. Ananta, can't put that past him. And we were able to demonstrate that here. This is a released MEMS GaN resonator, and HEMTs, resistors, and so forth, all fabricated side by side. The first monolithic GaN oscillator reported at ISSEC, and but that's just step one. So leveraging HEMT technology, right? That's typically used for RF, for high power applications, but now building in MEMS capability into it. We have since been working with companies like Swegan. They're based in Sweden, but have a beautiful platform where they have this epitaxial gallium nitride on silicon carbide that's basically buffer free. So they make a really thin GaN that's got a beautiful atomic transition to the GaN. They do that for RF and for high power applications, because that buffer is a thermal insulator. It's got all these awful dislocations that prevent that prevent thermal conductivity down into the silicon carbide and out of the chip. And so they work a lot to get that thinned down. That thinning down, the high quality of the gallium nitride, and the low or high thermal conductivity all translate to allowing us to scale gallium nitride, which is a piezoelectric semiconductor, up to 15 gigahertz frequencies and above, and to do so with very low propagation loss because it's so pristine, and to be able to support 60 dBm of power handling, because that heat that's generated, whether it's from the RF signal or from the vibrations themselves, they sink down, that sinks through the silicon carbide, which is a beautiful thermal conductor, very nicely. And we can think about filters for wireless communication in that space. So that's just a start. Gallium nitride is one capability, but if we're going for the best material for the job, let's really dig in Sandia National Labs developed a gallium arsenide on lithium niobate stack. And the beautiful part there, so the gallium arsenide has all the active devices that you'd want with high mobility and so forth. The lithium niobate gives us access, which is a piezoelectric, strong piezoelectric, gives us access to surface acoustic waves. And with this, you can launch acoustic waves, have them interfere with these active devices right at the surface. And when you have a piezoelectric wave, it generates a deformation potential, basically electrostatic potential, right? That causes bunching of the free carriers up in the gallium arsenide heterostructure. You can make high electron mobility transistors in that. Those bunched electrons have their own electrical field distribution that then acts back on the wave, on the piezoelectric wave, and you have this exchange of energy between the acoustic wave and the free carriers. So with that, you could do a lot of interesting things. One, you can attenuate the wave depending on how fast the electrons are going relative to the wave. One drags the other. Either you can pump energy from the electrons into the wave, amplifying the wave. You can attenuate the wave by reducing the velocity of the electrons. You can tune the velocity of the wave and therefore the frequency or the phase of the wave as it's propagating, and do a whole bunch of RF signal processing associated with all of that, amplifiers and so forth. And we were even able to demonstrate terminal gain. So I launch an acoustic wave, I pass it through basically this 2D electron gas where I'm running a current through it, DC current, and then get positive gain out of my acoustic wave at the output. So very exciting opportunities for radio front ends that way. And it's a non-reciprocal process. My electrons are traveling this way. If my wave is traveling this way, it gets amplified. If it's traveling that way, it gets attenuated. So you get isolation between one port and the other. And you don't need ferromagnetic materials and so forth to get there. So lots of exciting opportunities in platforms like this. All right, so to wrap things up, basically, there are a lot of opportunities leveraging MEMS and CMOS side by side. If you break that barrier, right, not only if I can get CMOS, hack CMOS in order to make MEMS devices, not only do I democratize MEMS, lowering the barrier for MEMS to be able to use different platforms, but now I've actually increased functionality of my integrated circuits, bringing in LC tanks, clocks, filters, sensors, and imaging all on chip in a technology platform that already existed. So given our need to develop micro-manufacturing capabilities here, now I'm saying I don't need a separate foundry. I don't need extra packaging. It's all built in and that capability is here. But it'll be much better if we can work with the foundries, develop materials that they're already developing and make them work best for this added functionality. So, thinking about access and thinking about collaborations moving forward with industrial research and de-risking those foundries to enable that kind of work, thinking about 5 years down the line, staying competitive. There are excellent opportunities not only for building that in a monolithic way, but leveraging heterogeneous integration and the best material for the job. All right. Finally, I'm going to monopolize this platform for 3 seconds just to mention the MEMS conference coming up in January in Austin, Texas. This is IEEE MEMS, where if you have any research that's relevant to any of that, or if you want to check out what the MEMS community is doing in this space, but in many others, come check it out. Full disclosure, I am co-chairing the conference, but we'd love to see, it's too late for abstract submissions at this point, but if you have an open poster that might be relevant to the MEMS community, whether it's work that's not yet prime time for publication, but you'd like to discuss it with the community, maybe for collaborative purposes or just feedback, or if you have those awesome results that you're making for a journal, but the MEMS community could really benefit from seeing it, just shoot that my way and we'll get you guys at least evaluated and seen. But come check it out, even without a open poster. We'd love to have you guys there. All right, and with that, I'll wrap up. I'm happy to take any questions. Thank you so much for your attention.
Thank you, Donna. Let's thank our speaker. So let's maybe take 2 questions, and then we'll open it to the reception, and there's going to be more time for discussion. So any questions in the audience?
Hi, Dana. I'm William Zhu, and that was a great talk. Earlier in the talk, you mentioned that lithium niobate and the aluminum nitride aren't CMOS compatible, but later on with all of this stuff, with all of these other 3-5 materials and so on, is there sort of a way to integrate that with CMOS processes, or what's the deal there?
Integrate lithium niobate or these other materials? The
other materials you mentioned at the tail end of your presentation.
Yeah, okay. So in terms of gallium nitride so with gallium nitride, actually we had a program with Raytheon, and Tomas Palacios here has had an effort in that heterogeneous integration of GaN and CMOS. There are certain limitations in terms of the materials and modifications to the process, but it's certainly possible when you get rid of the gold, for example, the gold omics for gallium nitride technology. People have figured out how to do that. Tantalum is a great alternative. And so people are working on all of those things. Niobate is more of a challenge. It is pyroelectric. It has a relatively low Curie temperature. And so there are certain limitations on that front. This is where the chiplet solution is really attractive because you don't have to worry about thermal budget in the same way. And you really focus on those heterogeneous interconnects, and there are challenges there too, but there's fantastic technological advancements to get us there, and I think that's a really great opportunity moving forward. Yeah.
All right, thank you.
Any other questions? So if not, let's thank the speaker again. We'll open it to the reception and she'll be here and can have further discussions. Thank you.
Perfect.